Again, class. This is the second lecture of this course, Database System Principles. Um, in the previous lecture, we talked about disks. So at this time, you should understand how disks work, in particular, uh, how um, what's the process of reading or writing information on the disk. Um, One very important message, takeaway message from the previous lecture, is that um, you know, whenever you talk about disk accesses, they are always expensive. And in fact, they're so expensive that people um, people have been um, accessing information in the unit of blocks rather than words. So that's the key difference um, between disk-oriented algorithms and CPU-oriented algorithms. Okay, so for CPU-oriented algorithms such as quicksort, merge sort, binary search, those algorithms are able to access words. You can go to a particular memory address and read the words there, read the word there, just one word. But this is not done on disks. On disks, you always access the whole block of data in one I/O. Okay, and the this significant difference in principles has far-reaching impacts on database systems. And today we'll look at one aspect of those impacts. You will see um, how you organize data on disks actually makes a difference, makes a significant difference in some cases. Okay, so this is what we're going to talk about today. In particular, I'm going to talk about two modern ways for database systems to store data. The first one is called row store, and that's the um, I would say the more popular way to organize data, and we'll see about this very shortly. And the other approach, which is called column store, is newer, and you will also be able to see, what are the motivations behind this new approach. Okay, row store versus column store. Okay. Um, this is something from the prerequisite of this course. You should already know what a relation is. A relation, sometimes people call it a table. A relation or a table consists of tuples, okay, tuples, or rows. All these are um, synonyms. And every relation has a set of attributes. These are the columns, okay? And these attributes together, they constitute the schema of this relation. So here we have a little example. This example one, this is a SQL statement for creating a table. As you can see, the name of the table here is customer. And this is a table with four attributes, and they are customer ID and the customer name, date of birth of this customer, and also, the government ID, right? When you create the table, you also have to specify the data type of each attribute. So for customer ID, as you can see, this is being declared as an integer. We also have something else here to indicate that this is the primary key. So every customer will have a unique value on customer ID. And the second attribute is a string, a text string, and the text string has 100 characters. Okay, and it cannot be null. You have to enter a value for everybody. So date of birth is of the type date. So this is a built-in type in the database system. Again, it cannot be null. And finally, we have a government ID, and this is a string with 20 characters, and it cannot be null. And also, this is a candidate key. All right. So again, no two customers can have the same value on this attribute. So as I said, these four attributes together, they form the so-called schema of the relation. Okay, schema. And the relation, contains many rows, right? So these four attributes are the columns. So this should help you recall the notions of rows and columns. And in this lecture, we're talking about row store and column store, right? So now you can already start to connect the dots. All right. So we have to store information. We have to store the tuples. In the end, everything will have to come down to bits, right? Our computers today, they are binary machines. You have to rely on binary encodings to represent values. So here, same statement, but with some comments. Okay, so these are not part of the SQL statement. However, they are useful remarks. And let's look at these remarks. Okay, so here are my remarks for you. Now, this is just telling you that in a database systems, typically you use 4 bytes. So that's 32 bits, right? 1 byte is equivalent to 8 bits. So you use 4 bytes to represent an integer. So you can imagine every customer ID will appear as a 32-bit integer on the disk. Okay. So character 100, and oftentimes a database system would use 100 bytes to represent such a string. Okay, so you can see the 100 here is being declared here. So every character occupies 1 byte. Okay, there are exceptions. Some database systems would use more bits to represent a character, but in this example, it's just 1 byte, okay, 8 bits. Date of birth requires only 3 bytes. Okay, 3 bytes. And the government ID, once again, is a string, and 20 is the declared length here. So every government ID requires 20 bytes to represent. Okay, so you can imagine this is true for every single tuple, and therefore each tuple requires how many bytes to represent overall. So you just add them all up, right? So the answer is 127 bytes. Okay. So this is really the physical representation of what you see in the tables. All right, there are no secrets, right? So in the backdrop, you really have to store a lot of values, and all these values typically appear in a file, okay, somewhere in your operating system. Okay. Well, here is a little remark. If you declare a table like this in a real database system, depending on what system it is, right? Let's say PostgreSQL or MySQL or Oracle, et cetera. And sometimes the database system will inject certain extra information into the tuples. Okay, so this information is controlled by the system. For example, many systems would automatically give a row ID to every tuple that you insert into the table. So this row ID is system controlled because it's not something that's explicitly declared in your SQL statement, right? The system would like to have this information because its implementation, or at least some part of it, will depend on it. Okay. So in our discussion, we typically will not be bothered with such kind of extra information. So the most important thing here is to get the main idea, right? Once you have already understood what is going on, extending your understanding to cover such kind of extra attributes is quite easy. It's quite straightforward. Okay. All right. So I think we're ready to talk about row store. As I mentioned, I'll be talking about two ways to organize data, row store versus column store. So this is the first approach. Okay. I'm going to be using the running example that you saw earlier. However, before I continue, I'd like to remind you about some important concepts that we learned from the first lecture. So first of all, you know the hard disk, right? Before you can use the hard disk, you have to format the hard disk. The formatting basically, cuts the disk into disjoint blocks. Okay, so block is the unit of access for the operating system. In other words, every time the operating system, by the way, when I say operating system, I mean your database system, because your database system lives in an operating system. Okay, so whenever the operating system will have to read or write something from the disk, it will always have to be reading or writing an entire block. Okay, so we spend a lot of time talking about this, and at this moment, you should understand why this is happening. Okay, so that's the notion of block. And as I said, right, every block is equally large. Each one of them stores the same number of bytes. Okay, the same number of bytes. And this number here is referred to as the block size. Okay, block size. And the symbol I'll be using is a lambda here. Okay. Um, a typical value for block size is 4K bytes. Okay, 4K B. So that's 4,096 um, bytes. Okay. All right. So now let's proceed. Um, and let's try to keep our discussion general. So here you can have an arbitrary relation. Okay. So this relation is denoted as R here. It can be any relation. And this relation, as I said, it's a schema. It has a schema, and the schema contains a number of attributes, right? So let's just say that the number of attributes in this relation is D. And I'll denote those relations as A1, A2, all the way to AD, okay? And for our discussion, I'll also need the number of tuples in this relations. In this relation, by the way, this D is the number of columns. Okay, N is the number of rows. Okay, so let me draw a little bit here. Okay, so this is an illustration of this D and this N. Okay. Okay, and so you have n tuples here, and I'll refer to the ith tuple. Let's say this is the ith tuple, and this is ti. Okay, so if you have to enumerate the tuples, it goes from T1, T2, all the way to Tn. Okay, good. Well, now let's talk about row store. So row store says, I'm just going to store the entire relation in a list. Okay, so this is a very important way to see it. It's a list, all right, because a list implies there is some sort of ordering one after another, right? Now, what is this order? So as you can see, the order is pretty straightforward. You store the first tuple first, and then followed by the second tuple, the third, etc., and then until you reach the last tuple. Okay, so it's a list, right? Now within a tuple, you list out the attributes from 1 to D. Okay, so you can imagine this as a file. Okay, so you have a long list of values, right? So let's say I have a little example here for you. Say this is just a simple example. Say you have only two attributes. So this is A1, A2. Okay. So the first tuple has value 1, 1 on attribute A1, and this tuple has value A1, 2 on attribute A2. Okay, and then you have another tuple. This is the second tuple, so A2, 1 is its value on A1, and then A22 is its value on A2, etc., right? So let me give you one more tuple. So this is 3, 1 and 3, 2. Okay, so you can store these 6 values in the following list. So the list would go like this. Okay, so A11 and then A12, right? So these two values, they form the first tuple, right? Okay, and it continues with A21, A22, okay, A31, A32. Okay, so you can imagine a file containing these 6 numbers. Okay, so this is row store, right? This is pretty straightforward, isn't it? Basically, you enumerate the values in this table row by row, right? And in each row, you go from left to right, and that's it. Right? Okay, nice. Now, let's drill into this. Okay, so here I have a little bit of calculation for you, but instead of talking about this immediately, let's first look at an example. So in this example, the customer table I created, okay, with this SQL statement, right? You still remember that statement. So we created that table, and I also spent some time going through every single attribute and telling you how many bytes would be necessary to represent the attribute. If you still remember, in total, every tuple requires 127 bytes to represent. Okay, good. And let's just assume that our block size, this operating system thing, right? This block size is 4 KB. Okay, 4 KB amounts to 4096 bytes. Okay, and here a question I'd like you to understand is how many tuples can fit in a block? Okay, so this is basically what's being calculated here. But continuing the example, the calculation is can be understood very intuitively as follows, right? So this is the total block size, and this is how many bytes you would need, the tuple size, right? How many bytes you would need to represent a tuple. So if you calculate this ratio, it's a 32 point something, okay? But you cannot really store a fraction of a tuple, all right? So this is something that you would like to keep in mind. In database systems, for various reasons, it's not such a good idea to allow a tuple to really span 2 blocks. Okay, so we want an entire tuple to fit in 1 block, all right? So if you calculate the ratio, you get 32 point something, but you don't want to do that. You don't want tuples to stride, over the blocks, right? So you don't want them to span 2 blocks. So you take the floor. Okay, so 32 point something becomes 32. Okay. So you might wonder, hey, maybe we waste a little bit of space. You're right. Okay, so some of the space will be wasted, and but there are important reasons for this. Okay, so it allows you to it allows the system to do many other things more conveniently. Okay, so it's I would say it's worth it. Okay, anyway, so it's part of the design. Okay. You could, if you want, you could in the future, you could rewrite this part. You could also utilize that part of the space, but then you also have to change a lot of other lines in the code. Well, whether or not this is something worthwhile to do, well, it's entirely up to you. Okay, and I, for one, would try to avoid it. Okay. All right, now let's go back to the general calculation. If you understand the rationale behind this, and then it should be fairly straightforward for you to understand what's going on here. Okay, so here every tuple has the length of L. Now this is measured in terms of number of bytes. So this L in my little example here, this is just 127. Okay. Now remember, this lambda is the block size. So if you calculate the ratio, you want to take the floor here. Okay, so this gives you the number of tuples that can fit into one block. Okay, again, the principle is you don't want a tuple to span more than one block. Well, some students at this point would start to challenge me, which is a good thing. So here we assume that this L, which is the tuple size, right? Tuple size is less than or equal to lambda. Okay, so lambda is the block size, right? So in this case, since a tuple is smaller than a block, and therefore it's okay to require that no tuple should span more than one block, right? So some of you will say, well, what happens if lambda is greater than L, right? So let's say this L was 2000, right? Sorry, so not 2000, 5000. Okay, 5000 bytes. So in that case, if the block size is 4 KB, and then you will have to allow the tuple to spill over, right? To spill over just one block. Well, yeah, you're absolutely right, but this is one of those, straightforward extensions, right? For example, if that's the case, you could put together multiple blocks, concatenate them into one larger block, right? And then, when you um, analyze things, you can assume that the database system will always write multiple blocks at a time, so that you don't really have this issue. Okay, so this is indeed how the issue is handled in practice, and also the reason why this is not such an important issue that warrants a lot of discussion in the classroom. Okay, just so you know, right? So if L is larger than lambda, you just put together enough blocks, and then you have one super block. Let's say this logical block uh, contains uh, um, more. I mean, these logical blocks have enough bytes to represent a tuple. Okay, and then you can apply what I just said. Right. So this is the first remark. Now, another remark is in reality, a database system would typically store some additional control information within each block. Okay, so this is usually referred to as the header field. Okay, header field. Um, yeah, so, well, this header field, there are no standards for it. It really depends on how the code is written. Um, so in our discussion, we will not pay a lot of attention to this typically. Once again, this is one of those straightforward extensions. Once you understand what's happening without the header field, and then you can just adapt your calculation. If someone tells you, say a certain number of bytes will have to be set aside for a story and a header. Okay. All right. Now, so let's look at this number, right? So this is like one block. Okay, one block. We're just talking about one block. And how many tuples can you fit into one block, right? But remember, in total, you have n tuples, right? You have n tuples. So the denominator here tells you how many blocks can fit into, sorry, how many tuples can fit into one block, right? But in total, you have n tuples. So if I ask you, I mean, how many blocks do you need, the minimum, right? Smallest number of blocks that you will need in order to store all the n tuples in the relation, the answer should be this. Okay, so what is important to note is that here you should be taking the ceiling, not the floor. Okay, so here's let's continue the example. This example is going to help to clarify it. I told you before, here I told you before, right? This 32, right? So this 32 is the number of tuples that can fit into one block, and let's just say that the customer table has 1 million tuples, right? So you can fit 32 into one block. So how many blocks do you need? Well, you will need rough, if you calculate this number, this is 31249 point da da da. Okay, so if you just calculate the ratio here, okay, but the number of blocks is always an integer, right? So if you get a fractional number like this, you have to take the floor. Okay, you have to go up to the nearest integer, right? And therefore, the answer is what you see here. This 31250, and that's the reasoning behind this stealing. Okay, you know you it's a terrible idea to try to memorize this. Okay, so because this is not something to be memorized. That's just not the way to go. Okay, you want to comprehend this, and then you can just write out the expression on your own, right? So um, to me, there's no room for confusion, right? So even if you apply calculation step by step, you will reach exactly the same expression by yourself, right? So you see, we have a floor here, but we have ceiling here, right? But there are very important reasons for each operation, right? Okay. So now let's look at some cost estimates. You already know that the customer table requires so many blocks. This is the number of blocks to represent, okay? Now, this is a SQL query. You have learned SQL queries from your prerequisite course, right? So I'm not going to explain what this query, the syntax behind this query, except to say that this query displays everything, retrieves everything from the customer table and displays the information on screen, right? So now, for the very first time in this course, I can ask you, what is the I/O cost of this query? So this question at this point should be perfectly clear. Okay, so if you look at all the terms in the question, all of them have been properly defined, right? I have defined what it means by I/O cost, and you understand why we're talking about I/O cost, right? So one I/O um, performs a read or write, reads a block or writes a block, right? And you also understand, why this has to be the case, right? Because this disk mechanism that I explained in the previous lecture. Okay, now apply your own reasoning in a straightforward manner. I'm sure everybody will come to the answer, right? So this is the correct answer. This is just the total number of blocks in the relation, right? So imagine you have the relation stored in a file, and this file occupies so many blocks on disk, and you have to read all of them to answer this query. Okay. So this is a very, very simple disk-oriented algorithm. So this algorithm simply reads all the blocks in the relation. Okay. So the cost is this much. Okay. Now, next query is kind of interesting. The next query says, okay, so what if I don't want star? Okay, the star means all the attributes. And what if I don't want all the attributes? Instead, I want just the date of birth. Okay, so you have to remember date of birth is much smaller in size. If you rewind the video, if you look at my lecture slides, by the way, you can find these slides on NTU Learn, right? You will see every date of birth occupies only 3 bytes. Okay, so intuitively, you are retrieving much you're displaying, let's say, you only need much less information, right? Just date of birth, right? Rather 3 bytes rather than 127 bytes for the entire tuple, right? Okay, so this query says display the date of birth of all the customers. Okay, so the interesting thing here is to think about the I/O cost, right? I mean, intuitively, you are retrieving less information. So people, I mean, students, especially people, that are exposed to this for the first time, would bring in the main memory mindset, right? So if you go by word accessing, yeah, you only need to access much fewer words, right? But does it mean you can do fewer IOs, right? So you already start to feel, I mean, you should be feeling there are indeed some very intrinsic differences between disk-oriented or IO-oriented algorithms versus CPU-oriented algorithms, right? So the answer is still this much. If you think about it, right, this DOB is scattered into a lot of blocks, okay? So the necessary IO cost to answer this query is at least the number of blocks that contain the information you want to retrieve. Okay, so and this DOB, as I said, is scattered across so many blocks. Okay, and what's really happening is that each block will contain information that's useless for this query. But there's nothing you can do about it. You still have to read the block, right? There's no way to go around it, right? You still have to read the block. The access unit is block, right? So you either don't do anything, don't read or don't write, or every time you read or write, you have to do it for the whole block. You cannot just say, I need only a little bit from this block, so I pay less. There's no such a thing. Okay. Yeah. So when you perform a block, most of the information would be useless, but you just have to deal with it. Okay. And still have to pay 1 IO for this operation. Okay. So if you go through the reasoning, you should convince, it's very important to think through this. Okay. So that's why I put this thing here, right? So I want you to think about this. It's very important to see the query cost is still the same, even if you are not doing all the attributes, you're not retrieving all the attributes. Okay. So there's one more sentence in this example. This is row major, right? So row store, right? So what's nice about row store is that every tuple fits in one block. Okay, so if you already know the address of that block, and then you can just go to that block and fetch the information of this tuple, right? So only 1 IO is required, okay? And once again, provided that you know the address of that block, okay? So this is something nice about row store, okay? So you need one tuple, just 1 IO. Very nice. Okay, so now that brings us to column store, okay? So you will see row store and column store, they complement each other. It's not like one approach is a slam dunk winner overall. Okay, no approach is absolutely better than the other. I will introduce you to some pros and cons later, right? But it's very important to remember, right? It's not like, okay, column store is a newer concept and therefore it's something absolutely better. No, okay. So these two approaches, neither one of them dominates the other. Okay. All right, so column store, let's have a formal view about it. Okay, so as before, I'll be needing some symbols. So this is the relation, and again, we have D attributes in this relation. And here we have n tuples inside the relation, and I'll use Ti to refer to the ith tuple. Okay. If you remember in row store, I repeat row, okay, not column. Row store, we needed only one list, okay, one file, all right, because it's a big file containing the tuples in tandem, right, in sequence, in tandem, right? So one after another, okay? Well, in column store, the story is different, okay? So if you have, say, D um, attributes, and here is n, right? N tuples. So what you want to do is uh, you want to order the values by columns first. Okay, so this is the first column, and that's for attribute A1. Okay, so for this column, what you want to do is you want to store a list L1. Okay, so this L1 contains only the information on A1. As you can see, right? So this J, in general, this J goes from 1 to D. So when J is 1, now you see this AJ, right? All of them, they are A1. And here, this is a list on its own. Okay, so you can imagine there are D lists here, and this is the first one. And this one contains nothing but attribute A1. Okay, so you want to store all these things into one file. Okay, well, of course, you do this to every other attribute. So you have another list. That's L2. So this L2 stores nothing but A2 values. Again, the ordering matters. Okay, in this list, you have to really, really respect the ordering of the tuples. Okay, T1, T2 to Tn. This is important for information retrieval. So this is something we'll talk about later. Okay, and you have in total D lists, right? So L1, L2, all the way to LD. Okay, all right. So this is column store. Okay, as the name suggests, you can imagine you were um, arranging the values in the table. In row store, you want to do row by row, but here you want to do column by column. Okay, so if you think about the original idea, this is fairly simple, and therefore it's quite surprising to see that such a simple idea turns out to have deep impact on database systems, and we'll see about that. All right, now let's talk about some math, though. So we got to understand, for example, how many blocks will be needed in each file. Okay, so remember how many files you have. You don't know you no longer have just one file. You have D files. Okay, so D files if you have D attributes. Okay, now let's look at each file. So here there's some typo here. So this is not I. Okay, so this is J. Is I want to be consistent. So J is for columns, and I is reserved for rows. Okay, so we'll come back to the expression later, but before that, let's look at some example. Let's look at some examples. Okay. So here, once again, we're talking about the customer table, and if you still remember, name is an attribute of that table. And every name is declared to be a string with 100 characters. Okay, so this requires 100 bytes to store. Okay, so if the block size is 4 KB, okay, and then if I ask you how many names, just names, right, no other attributes, how many names can fit into one block? Well, the answer is, well, you calculate this ratio. Okay, you calculated this is 40 something, right? 40.96, almost 41. Okay, but not quite. Okay, so 40 something. So how many values can you fit into one block? Well, the answer is you have to take the ceiling, and therefore you can fit 40 values into one block. Now remember, all these values, they are for the attribute name. Okay. And this calculation will give you different answers for different attributes. So here is another example, this is date of birth, and date of birth requires only 3 bytes to store. So if I say, okay, how many date of birth values can you fit into one block? The answer is, block size divided by 3. So this is 1364 point something, right? So you have to take the floor here. Okay, you don't want a single value to span 2 blocks. Okay. All right, now let's come back to the calculation here. This says if you talk about attribute AJ, right? Attribute AJ, and you need LJ, okay, LJ bytes to represent a value. So for example, if attribute AJ is name, and then LJ would be 100. If attribute AJ is DOB, and then LJ will be 3. Okay, so the expression calculates how many values you can fit into one block, right? So the reasoning is pretty much the same as what you saw before in the row store case, except that here we're talking about how many values you can fit into one block rather than how many tuples you can fit into one block. Okay. Good. So once again, this is a typo. So let me correct this. This I should be J, and also this I should be J. Okay. So all the occurrences of I should be J here. Okay. So this is also J. Okay. Okay. So this is calculating how many blocks you will need to represent each column. Okay. Let's see some examples. Here we're still talking about a customer table, and let's assume that the customer table has 1,000,000 tuples, right? So the block size is 4 KB. All right, now it really depends on which attribute you're talking about. If you're talking about the customer ID, okay, customer ID is an integer. Okay, let's recall. Customer ID is an integer, and integer requires 4 bytes to represent, right? So if you calculate how many values, how many integer values you can fit into one block, the answer is 1024. All right, so that's how you get this 1024. But how many blocks do you need in order to store the whole column? So the answer is, this number of tuples and divided by how many values you can fit into one block, and then you get a fractional number. But then this time you have to be taking the ceiling. Okay, so the reasoning is exactly the same as what we saw in the row store case, right? Okay, but remember the answer is different for different attributes because different attribute values, they have different sizes. So for name, it's longer, right? So it requires 100 bytes to represent. So in the previous example, we calculated this 40, and this is the 40 showing up here. So the number of blocks is 1,000,000 divided by 40. But again, you should be taking the ceiling. But in this case, it's just no fraction, right? So this is just a perfect division here. So this is a integer division. So that's easy. For date of birth, we calculated before. Every block can store this many values. So how many blocks do you need to represent the DOB column? So the answer is this. So you get the number, and similar calculation applies to government ID. Okay. So I guess I don't have to spend time explaining this expression, right? So I think this is fairly clear already. All right, so this is the last slide of this lecture, and this is actually a very important slide because it allows you to tap into the differences between row store and column store, and also you'll be able to understand better the motivation behind column store. I told you, right? Row store is the more traditional approach, and then this column store came into being. But what was the original motivation for a column store, right? So that's another thing you will be able to see from this slide. One more thing you'll be able to see is that no approach is better than the other, right? So you will see some advantages of column store, but you will also see some major disadvantage about it. Okay. All right. So again, let's think about this query. This query is something we saw before, right? We want all the tuples in the relation. Okay. So in this case, you will just have to read all the columns, right? You have to read all the columns. So, and when you read all the columns, you have to be strategic as well, because this is not as trivial as in RAM, in memory. So you have 4 arrays, you have 4 lists, except that these lists, they are stored on disk, okay? And you have to remember they are blocked, right? So each list, is cut into blocks on disk, right? So this is an illustration, okay? So let me just give you all these blocks, continuing, right? So you might have many of them, okay? So when you answer this query, you have to put together the attribute values of the same tuple, right? You cannot say, hey, I just display everything on A1 and then I display everything on A2. It's not going to work that way, right? Because in order to answer this query, you really have to um, display information row by row. Okay, so you have to convert the column representation to the row representation, all right? And you have to do this carefully. Okay, to do so, you really have to go through these lists in a synchronous manner. Okay, you have to read them all together. Okay, so when you are when you are at the first block of each attribute, and then you see the values of the first tuple, right? So you read these 4 blocks into memory, and then you can put together the 4 attribute values of the first tuple, right? So you can put, now you can have the whole tuple for display, okay? And then after you are done with that, you want to continue to the second tuple, right? So you put together the information of the second tuple in the main memory, and then you display the tuple on screen, right? Now, eventually, you will run out of tuples in the main memory. So that's why you will have to continue reading the file, right? So after you have exhausted the values of one attribute in the main memory, you have to read the next block of the corresponding file to bring the content into main memory, right? So everything will have to be concatenated, everything will have to be put together inside the main memory, okay? Now, something that is important to note is that, these files, they have different lengths, okay, different lengths. So that's why I said the scan of these 4 files, the scans of these 4 files will have to be done in a synchronous manner, okay? However, you will progress on these files at different paces, okay? Because like DOB, right? DOB is the smallest attribute. It takes only 3 values to represent a DOB value, so you have much fewer blocks on DOB. Okay. And on the other hand, this is for name, and name, you have a much longer file, right? So you can imagine you will be reading more blocks as you go, right? Because you have to go really, really by tuple. So these 4 pointers, they 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 charge ahead, right? But at different paces, right? But what keeps them together is the row ID, right? So at any time, you will be probably keeping uh, this block in the memory about ID, but this block about name, and maybe this block about DOB, and maybe this block about government ID. You see what I mean? So at any moment, you will be needing just one block in the main memory, right? You don't really have to keep all the blocks in the main memory, right? So the blocks that have been processed can be evicted from the main memory, right? So after all, your main memory is much smaller than than the database, much smaller than how many blocks you have in the files. Okay. So if you do this, and then eventually you can answer this query by scanning these 4 files in just once. You don't have to scan them twice. Okay. So the I/O cost is the total length of all these files. So if you compare this number to the number um, that you saw in row store, these two numbers are comparable. Okay, with this number maybe slightly higher in this case, but this is not always true, right? Sometimes row store, the number for row store will be a little bit higher, and sometimes it will be a little bit higher for column store. This is not really a disadvantage, all right? You will see a more severe disadvantage for column store, but this is not it, okay? Even though this number here is slightly higher than row store. Okay, now let's move on to the second query. Now this is giving you one of the major motivations for column store. Okay, so here we want only DOB. Okay, we don't want other attributes. So in this case, obviously you don't have to read all the files. There are 4 files here. There are 4 lists here, right? You don't have to read all the lists. All you have to do is to read the list of DOB. Okay, and this is beneficial because the DOB file is much shorter, right? DOB, every DOB values, let's recall, requires only 3 values to represent, right? So altogether, you have only 700 something blocks in the file. So how many IOs would you be performing? You have only 733. Okay, you still remember in the in row store when we came here, when we came to this point, the number of IOs. Still remember how much? Still remember how much it was? It was the same as the IO cost for answering the first query. All right, so it's more than 30,000, right? So this is much smarter, and this gives you a significant advantage for a column store. Okay, so this is very intuitive. This makes a lot of sense, right? Column store is very good if you want just some columns, right? But in certain applications, this is the case. Okay, so you could you might have lots of columns, but an application typically, each query would just focus on a small subset of those columns. All right, now finally we come to this sentence, and this sentence gives you a major disadvantage of column store. Okay, so say I want information just one tuple. In row store, we have this nice thing that every tuple fits in one block entirely. Okay, no exceptions. Okay, because it's a row store, right? So row comes first, right? However, this is not the case for column store. Okay, so if a tuple has 4 attributes, and those 4 values, they typically they are stored. Actually, not typical. I mean, almost always they are stored in 4 different blocks. Okay, so in order to put together information of a tuple, you really need to read those 4 blocks. Okay, so you'll be needing 4 IOs, and that's a big difference, right? 1 versus 4. In fact, this number goes up linearly with the number of attributes, right? And in column store, typically column store would have significant advantage if the number of columns is large, okay, very large. Okay, if the number of columns is small, it might still give you certain benefits, but you will have less benefits. But column store will be particularly attractive if the number of columns is very large. Let's say you got 100 columns. But on the other hand, most queries will focus on just a small number of columns, right? So in those scenarios, column store will make most sense. However, even in that scenario, you still have a major disadvantage, all right? You always suffer if you want all the information of a particular tuple. Okay, so if you have 4 attributes, and then you will require at least 4 IOs to put together a tuple. And if you have 100 attributes, you would need 100 IOs to put together a tuple. On the other hand, for row store, it's much less. Okay, so that's a comparison. Okay. All right. So this is the end of today's lecture. I hope you have learned something new. Okay. So that concludes the first week's content. All right. Thank you for listening, and I'll see you next week. Okay. Bye bye.